All right. So for the first part of 6.3 is about the fundamental theorem of calculus. And the key point of this is the Riemann sum. Riemann sum is the name of the sum. The sum here, that means you add terms together. We're going to start with the function y equals f of x is given, and the function has to be non-negative. That means the value has to be greater than or equal to 0. So this term, another way we call like non-negative. That means the graph will be above the x-axis, or the least case would be like equal to 0. So, and the function is also continuous. That means you have one smooth curve, okay? From this assumption, we have to know the bound of the graph, like from point A to point B. So we put the condition, so on the closed interval AB. That means we are looking for the area between the curve and the x-axis from point A to point B, just this portion. Okay, so that's the assumption. And the goal of the Riemann sum, or the objective, is to estimate, okay, to estimate the area under the graph or the curve or the yellow area there. Okay, and how do we do this? We're gonna do it by summing the areas of adjacent rectangle. That's why it's called the Riemann sum. And the key concept of this first step, like from the interval, so I'm put the step number 1, from the interval AB, that means the left x is A, the right x is B. So we're gonna find the equal width, which is called the delta x, or the increment is from B minus A, or the length from B minus A here, and then divided by the n. N is the number of the sub-intervals. So n is the number of the sub-intervals. Because the idea of this is we are going to break this up into small portion and make it as the rectangle, and we find the area of each rectangle. So we're gonna have to find out how many sub-intervals we're gonna use. That means how many, or the number of the n as the number of the rectangles that we break them up as the area under the curve between point A and point B, sub-intervals. Okay, so first of all, we're gonna find the delta x, or the increment, or the width of the rectangle. Okay, and then we're gonna choose the value to find the height as the height of the bar, the height of the rectangle. Gonna be the function value at the point C. Okay, if you look at this as one bar, so that means you have the rectangle, okay, that you have like many of them, right? So for one piece here, the height of the function is the height of the bar. I mean, the value of the function is the height of the bar. And then the increment here, the delta x, is the width of the bar, or the width of the rectangle. And when you find the area is the width times the height, which is the delta x multiplied by the function at the point C. And the key is the point C, it could be as identified as the midpoint, or the left endpoint, or the right endpoint. Okay, you have choices. The problem should indicate very clear whether the C is as a midpoint or C as the left end or C as the right end. For example, for the midpoint, if you look at one bar, the C is right in the middle of the left X and the right X, okay? And for the left end, for one bar, the function value here, this is X equals C. So this is a function at C, that's the left end. For the right end, it's similar way, but you're gonna use the height of the function as X equals C on the right end, so F as C. So I'll use an example to explain more detail. So this is kind of the concept of the Riemann sum as a fundamental of the calculus. Okay, if you break it up into equal subintervals, that means you have the equal width for each rectangle. And then this is just one area for one rectangle. But you have like many of them. So as the sum of all rectangle gonna be the estimated value of the area under the curve. So this can be the sum of the width times the height, okay, as a concept, and I'll wrap it up in a little bit. So that means in the graphical way, you have the curve and you break it up from point A to point B. Okay, break it up into equal subintervals. For example, in this case, we have like 4 of them, okay? And then this gonna call like x0, and then next will be x1, x2, x3, x4, or xn as the last point or the right end point. And then for to estimate the area, if you use the midpoint, so you're gonna have to identify the midpoint of each bar, each subinterval. So over here, I call like x bar 1 as the midpoint. And the middle one here is x bar number 2. This is x bar number 3. And this is x bar number 4. And how do we use this? Since this is the function y equals f of x, so we're gonna form the rectangle. So the rectangle has the height and the width. So we're gonna use the point x bar, x1 bar here to find the height of that bar. And the same over here for the second bar, use it as the height of this bar. So this one is a function at x2 bar. And the next one, same way. So the height is a function is x bar number 3. And the last one, so that is the function value at x4 bar, or the midpoint on the 4th subinterval. And the area of the curve, the area between the curve and the x-axis is approximately equal to the sum of, I'll use this one as area 1, area 2, area 3, and area 4. So gonna be the sum of A1, A2, A3, and A4, where A1, the formula of the area, so A1 is the width times the height. Okay, what is the width? The width is delta x, and delta x is computed by b minus a divided by n. Okay, and the height is the function at each x bar. So for A1, it's gonna be the delta x as the width multiplied by the height, which is the function at the first midpoint, and the same way as the rest of them. So I put a parenthesis here, parenthesis, fx2 bar plus the delta x as a width multiplied by the function at x3 bar, and then the last one, delta x multiplied by f at x4 bar. And as you see, all of them have the common factor, delta x. So you take it out of the group. So this one is the delta x multiplied by the function at the first x bar, function at the second x bar, the third x bar, and the fourth x bar. So this is the area from the midpoint approximation, and they have the common delta x. Okay, so and the whole thing here is called the Riemann sum. The sum means you add them up, okay, and use the Riemann sum to approximate the area between the curve f of x and the x-axis, where f of x is continuous and non-negative. So the graph will be above the x-axis. So this is the midpoint. And for another two cases, so I draw the similar graph from point A to point B and break it up into 4 equal subintervals like the previous one. The graph might not match like point by point, but with this way, if we use the left endpoint, it's called left approximation. Let me see the key term in the notes. Use the left endpoint because each book they use different terminology, but the whole concept is the same. So this is the left endpoint. For the case of the left endpoint, we have the number of the n or the number of subintervals, the same setup. So then the delta x, which is the width of each bar, or the increment from one x to another x, is the left end minus the right end, or the b value minus the a value, all divided by n. So all three cases, you're gonna use the same formula. For this case, so this is the portion of delta x, and then the first one, we name it as the x0, and then x1, x2, x3, and this is x4 or xn. Use the left endpoint. It means for each interval, for each bar, you're gonna use, for example, for this interval, you're gonna use the left function value as the height of the bar, the f of x0. And then for the second interval, you use the left endpoint to find the height of the bar or the function value. So this is the function at x1. And then the next one, same way. And the last one, for all of them, you are going to use the left x to evaluate the function value for the height of the bar. So for the left endpoint approximation, you do not have to compute the midpoint or the average x value. You just take the left end of the interval, compute the function value. Okay, if you draw the real number line, so this is the x0, x1, x2, x3, and x4. For the left end, you are going to take the left except the last one. Okay, so when you take these 4, that means the area of the area under the curve f of x, or between f of x and the x-axis, is approximately equal to same notation, a1, a2, a3, and a4. Okay, a1 plus a2 plus a3 plus a4. These are the notation for the area of each bar or each rectangle. A1 from the length times the width, right? The width is the delta x. The width is the function at x0. And then plus, same thing, the delta x, the function at x1, the delta x function at x2, delta x function at x3. And again, the common factor, we factor it out. So then delta x multiplied by f at x0 plus f at x1 plus f at x2 plus f at x3. So when you work on the problem, and then draw the real number line, you can see very clear what set of the numbers you're going to use to compute the function value as a height for each rectangle. Okay, so this is the left end, and the right end is similar. So if I compare side by side, hopefully it's not too crazy in here. So I'm gonna use different color, but just hopefully I sketch close enough curve with the previous one. So from point A to point B, and break it up into the same number of the subinterval again. But this case, we look at the right endpoint approximation. How do we handle this? So the same way as compute the delta x, which is b minus a divided by n. Okay, this is x0, x1, x2, x3, x4. For the right endpoint, for the first interval, the right end is x1. So use that to compute the height of the bar. For the second interval, x2 is the, where did it go? New chair, whiteboard. This is the right end, the right end, the right end. Okay, from the same graph, the same setup, but the point that you use to compute the height depends on how it's indicated as the left, the right, or the midpoint. Okay, so you're gonna use the right end of each point. So that means the very first left not used. So x0, x1, x2, x3, and x4. You're gonna use this point, this point, this point, not the first one. And then the area is approximated by the sum of the area of the small rectangle. It keeps going back. So this one, if I name this as the A1, this is A2, A3, and A4. So the area, I'm gonna put a note here. So the area is approximately equal to the delta x as a common width, and the height can be the function at x1, function at x2, function at x3, and the function at x4. This for the right end and this for the left end. So it depends on what the problem asks you to do. And for each part, as you see, you're gonna lose some, you're gonna gain some. So those will combine to be an error of the estimation. Okay, so this is the concept of the Riemann sum or the fundamental theorem of calculus.